All right, so let's look at limits and derivatives. All right, so derivatives and rate of change. Now we discuss what we call tangents. Now if I give you a curve C that has equation, so let me get my pencil. All right, so the equation there is y equals to f of x, and we want to find the tangent line to that curve, and they give you a point, all right, P. It has entry A and then f of A. Take note, if I give you a point, the first entry is x, and obviously the second entry is f of that x value. So if the x value is A, therefore the y value is f of A, all right. Now, how do we find the tangent line? To find the tangent line, we should be able to know what the slope is, all right, the slope of the tangent line. And we do that by finding a nearby point. So this point I can call it Q. It has entries x and f of x. And take note, x must not be equal to a, because if x equals to a, then it means the point P and Q are exactly the same point, which is a bad idea. Now, how do we compute slope? We know that the slope is change in y over change in x, all right? So change in y over change in x. Straightforward and easy. Now, the question is what happens when Q approaches P? So let's see the sketch. So this is your point Q. The question now is what happens when it gets closer and close to P? Notice it, this X here at the bottom will be getting closer and close to A as well. So as Q approaches P, the point X will be approaching A, all right? So we can define slope now in terms of limits. And that is exactly what we're trying to say. So we see the tangent line to the curve y equals to f of x at the point P A f of A is the line to P with slope. So look at the slope now. We say m equals to limit as x tends to A, f of x minus f of A over x minus A. All right. And very important, provided this limit exists. All right. Because the limit does not exist, it means there's no slope. It's as easy as that. All right, so this is the definition you're going to use for now when we're looking for the slope of a tangent line, all right? Now, if you know the slope, obviously you should be able to find the equation of the tangent line. We use y minus y1 equals to the slope into x minus x1, all right? I'm sure everyone knows that. This is one question. So how would exactly that I'm asking you limit? So you need to be really careful, right? In the test, let's look at example one. They say find the equation of a tangent line to the parabola y equals to x squared. And then I give you 1 point. So I give you a curve, I give you a single point, all right? Obviously, for you to get the slope, you're going to use this definition there. You're going to use limit, all right? So limit is going to remember the first entry that stands for x, so it's going to be x approaching 1, and then f of x minus f of 1 all over x minus 1. All right, so I'm just applying the formula that we saw earlier. And if you substitute, you get something like this. Now take note, I told you before, when you're solving a limit problem, sometimes direct substitution may not work. In this case, if you put x equals to 1, you have 0 over 0, all right? Which means the slope doesn't exist, but that is wrong. You see what they're doing here at the bottom? You must factorize. So whenever you're solving a limit problem, even in my quiz that you're going to get on Friday, you need to start by trying to substitute directly. If you see that it doesn't work or it gives you something divided by 0, try and see if you can factorize, try and see if you can rationalize, follow all those rules that I taught you, all right? If not, you're just going to get the wrong answers as easy as that. In this case, you see that the top here is just a difference of 2 squares. So I can write that as x plus 1, x minus 1. And take note, x minus 1 cancel with x minus 1. And I'm left with limit as x tends to 1 of x plus 1, which is just equals to 2. Be careful, I didn't say find the slope, I said find the equation of the tangent line. So you need to use that formula y minus y1 equals to m into x minus x1. All right. So always read your question carefully. How do you know if you need to do limits? I give you a function or a curve, and then I give you 1 point. And then I say find the equation of the tangent line. You need to use, all right. Someone say, will it be wrong if I just differentiate? I know you've done differentiation. at this point in time, the assumption is that you haven't yet done differentiation. All right, that's the assumption. So if I ask you to find the equation of a tangent line at this point in time, obviously I shouldn't be seeing differentiation. All right. But once we do differentiation, then you more than welcome to use differentiation. All right. All right. Now look at this statement carefully. This one here in box. We sometimes refer to the slope of the tangent line to a curve at a point as the slope of the curve at that point. So the slope of the tangent line to a curve at the point, we can say that is the slope of the curve at the point. Why is that usually the case? Because if we zoom closely towards that point, you notice that your tangent line almost coincide with the curve. I'll show you something quickly. Look at this three sketch here. So this first one, obviously, if you look at the point 1, 1, okay, you can see there's a little bit of curve there, right? There's a curve that passes through that point. It doesn't look like a straight line. But if we zoom in more, how do you know if you zoom in? You must take note here you had 2, 2. So if you zoom in, that those value drop. So now you have 1.5 there, 1.5 there. It means you zoom in. Now, if you zoom in, compare these two curves. So this first one and this one, you notice that this is starting to look like a straight line. Okay, now zoom in even further. Look at what happened. It looks like a straight line, right? So that is why we always use that idea that the slope of a tangent line at a point is actually the same as the slope of the curve itself at that point. All right. Because if I draw a straight line, remember your tangent line is a straight line that passes through that point, more or less is going to coincide the curve itself. All right, it's going to look like the curve itself. All right, I've already explained this. All right, so this is another definition, which is just another way of finding slope. All right, in this case, we let h, so we let h to be x minus a. Obviously, if you make x a subject, x is just going to be a plus h. All right, so take note, if x is a plus h, it means that x1, if you start at a, you're going to have a little shift to the point a plus h. All right, and that point is going to coincide to the point q. Your slope now becomes f of a plus h minus f of a over h. All right. And then here they tell you that if h is greater than 0, right, it means that if you add some positive value to your a, obviously the point q has to be on the right of the point p. But if h is less than 0, it means you're subtracting something from a, your point q now is going to be somewhere there on the curve. It's going to be right on the left. All right. All right, this brings us to definition 2, which is very important. Why is this definition important? It's taking us close to something called first principle, all right? But we'll discuss it later on. I don't want to skip in any section, all right? So M here, which is still a slope, is limit as h tends to 0, f of a plus h minus f of a over h. If you use this formula or you use that point slope form that we did earlier in the example 1, you will get exactly the same result, all right? So both of them works. All right, this is another example you can go try. Again, I give you some parabola and then I give you 1 point, but this time I want you to use this formula here, all right? And if you do that, if you substitute and you simplify, you just get up to be minus 1 over 3. And then obviously to find the equation of the tangent line, you use y minus y1 equals to m into x minus x1. And take note, this 3 here is your x1 and 1 here. So this value here is x1, y1. So if you plug it in that formula, y minus y1 equals to m into x minus x1, you just get the equation of the tangent line. Right? Straightforward and easy. The memo for each of these examples that we're doing here is fully done. All right. The PDF is available on Blackboard. So if you can't do it or you don't get to these answers, look at the PDF. Derivative. All right. Now we get into derivatives. We already see something like find our slope. And now let's find the derivative of a function at a number a. All right. So by definition, we say the derivative of a function f at a number a is denoted by f prime of a. So if I say f, single prime, so single quote or you call it quote. So f quote a, that is just the derivative at that number, all right? It's the same as the limit as h tends to 0, f of a plus h minus f of h, all right? Similarly, you can use this, like I said before, you can use this, all right? But if I say use the point slope form, please just use the second one here at the bottom, all right? So number 5, equation 5 typically will be what we're going to denote as the point slope form, all right? It's what most of the time I expect you guys to use. If I give you a curve and then I give you a point and then I say find the slope at that number or at that point, all right? So we call this point slope form. But like I say, if you use any of these two, you get exactly the same result. This is another example. Here they're using definition 4. They say find the derivative of this function at the number a. Notice it, you just say f prime of a is limited, so you write out this whole statement there and you simplify. You simplify as much as possible. A will cancel with a squared, and if you simplify, there will be h that you can factor out. Let's see, yes, it works out. So you look at the simplification there, h is common. And if you factor out h, you cancel with the h at the bottom. And as h tends to 0, so this guy here tends to 0, you just left with 2a minus a. All right, easy and straightforward. Go practice. Okay, let's look at what they're saying here in box. They say the tangent line to y equals to f of x at a f of a is the line to a f of a whose slope is equal to f prime of a. All right, which is just called the derivative of f of a. All right, again, this is the point slope form. We've already seen it. Is that equation 5 that I mentioned? So y minus y1 equals to the slope, which is f prime of a into x minus x1. All right. So we call this point slope form equation of a line. Now for rates of change, what I'm just going to say is go look at it, guys. I will not be testing on this, but go look at rate of change, all right? Just for understanding's sake. Now what I want to do quickly, because like I said, we have to do 2.8 as well, is to go straight to 2.8. This is the exciting piece, all right? Again, 2.8 is limit and derivative. Now we go to derivative of a function. All right, derivative of a function. And the first thing we're going to discuss, remember we've seen this already. That's how we found the slope of a curve at the point A or at the number A. This time, remember that A is a specific number. All right. Now we want to generalize. We want a situation where a can be replaced with a variable x, so any number. So we want a general formula for a derivative of a function. That's why we use x, all right, because x can vary. And this definition you see here is what we call first principle. So take note about it, all right? If I say find the derivative and I say use first principle, I know you guys know too many stuffs of derivative, product, power rule, quotient rule, and so on. But if I insist in the test that use first principle, you must use this definition too that you see here. It's a must, all right? And I can tell you before, we always ask that first principle, so know what first principle is, all right? So it's this definition that you see here. Okay, let's see application of first principle. This is some nice, okay. Now they give us this curve and they say sketch the graph of the derivative. All right. This is a very nice question. I give you a curve and then I say sketch the graph of the derivative of that curve. Now you need to use common sense. All right. First you need to notice is if I to find the derivative or the slope at any point on this curve. So if we look at this a point here, notice if you draw a tangent line that passes through that point, you're going to have a negative slope. Why? Because that curve is decreasing at that point. Negative slope. Once you hit this bottom piece here, which is a turning point, all right, you're going to get a straight line. All right, if you draw a tangent line, there's just a straight line, horizontal line. The slope there is 0. Slope is 0 means it's just going to cut the x-axis if you actually sketch y prime or f prime. All right. Okay, so this is a more better explanation. You can see at this point A, B, C, the slope they are all 0 because just some horizontal line, all right. There you get a change in x, but you can't get a change in y. Remember, if you draw a horizontal line, you can only get change in x. The change in y will be 0. So 0 over any change in x is 0. That's why the slope there is 0. Now, now that you know what this 3 point is, it's easy to schedule. But now you need to know what happened at somewhere here on the graph, somewhere there, somewhere here, and this piece here. All right. Take note, at those points you either get increasing slope or decreasing slope. All right. When the curve is decreasing, you get a decreasing slope. When the curve is increasing like this stage here, you get a positive slope. Here you're going to get negative slope because you can see the curve is decreasing, and here you again get a positive slope. And if you sketch that, notice it at the point A, B, C, it cuts the x-axis at those points, all right, because the slope is 0. All right, so your f prime is 0, and what does that mean? It means at that point it cuts the x-axis. And this piece that you see here, so this piece here is just saying that I have an increasing slope, and then here you have some decreasing slope. Again, you have some increasing slope. All right. There are many examples like this in the textbook. Please go practice how to sketch the derivative of a curve. Okay, this is just explanation which we've done. Now, the full solution to example 2 here is on that PDF that I mentioned before, which is already on Blackboard. Go look at it. Find the derivative of f and state the domain. All right. Some of you get to the test, you read the first piece, find the derivative of f, and then once you get the derivative, you're done. Read everything. State the domain of f prime. It means you need to find the derivative, and you need to tell me what the domain is. All right. And remember, at this point, we haven't yet done the rules of differentiation, so the only thing you need to use is first principle, all right? But like I said in the test, I'll be so nice. I'll tell you guys when I want you to use first principle. If I don't mention first principle, you're welcome to use any method that you want to use, all right? But for some specific question, we might say use first principle. So go look at the solution. Like I said, it's already on Blackboard. Obviously, a polynomial, the domain is a set of real numbers. And for something like this, you can divide by 0. So obviously, the x has to be greater than 0 under the root, all right? Everything under the root has to be greater than 0. You can't say greater than or equal to, because you can't even divide by 0. Order notation. Now you need to take note. I don't want people to say, what does f prime stands for? So f prime means dy dx. It's just derivative. Y prime is the same as f prime. I can say dx, where f is your function. I can say df of x over dx. I can use capital D. So these two notation here, you mostly see it when you do math 2, because this is a notation we use, all right? But like I said, it doesn't change anything. If I say df of x, I mean derivative. If I say d subscript x, it means derivative with respect to x, all right? Usually we use this notation, this last one here, when we're doing partial derivatives, all right? All right, Leibniz notation. So Leibniz notation simply states that dy dx is just the limit as delta x approaches 0 of delta y over delta x, all right? All right, where is this coming from? It's coming from that rate of change that I said you guys to go. So that's just what Leibniz stands for. All right. And if you apply Leibniz notation at a specific number a, you can just say dy dx at, you see this line here, simply say at the point where x equals to a. Or you can use square brace and you say at x equals to a, it's the same thing, all right? Another student would just say f prime of a, it's the same thing. So this whole thing you see here, it just means f prime of a, all right? So you can write this or you can say f prime of a. But if you see this somewhere, don't get confused. So this is what they're mentioning. You see here is just f prime of a. So this whole thing is just f prime of a. All right, a function is differentiable at a if a f prime of a exists. So for a function to be differentiable at a number a, f prime at a must exist. Now, if it is differentiable on some open interval, this is where it gets a little complicated, only if it is differentiable at every number in that interval, all right? If I say, is this function differentiable at the point x equals to 2, obviously your focus is just x equals to 2, all right? But if I give you some interval, I say it's differentiable in the interval maybe 1 to 10. It means you're going to test for 1, you're going to test for 2, for 3, and so on, all right? You're going to test all numbers in that interval. All right, guys, I'm going to tell you, example 3, you should write down somewhere, nota bene, all right? Because definitely, you probably see this somewhere, all right? Where is this function differentiable? This one we always ask and people just leave it blank. So exciting, right? All right, let me go through it step by step so that you said you wouldn't tell me that I didn't explain. I explained it. If x, so remember this is an absolute value function, all right? We want to know where it is differentiable. The first thing you need to do is you need to use a definition for absolute value function. Absolute value of x means it can either be x if x is greater than 0, or it can be minus x if x is less than 0. So we start with the first case, if x is greater than 0. Then we know that absolute value of x is equal to x. All right. Now, remember, we haven't yet done those rules of differentiation. We have to use limits here, right? So we choose some h value which is really small enough so that x plus h is greater than 0. So if you take absolute value of x plus h, then you know that x is greater than 0, and your h is some small positive value as well, definitely it's going to be x plus h, all right? Therefore, for x greater than 0, how does the limit look like? You have f prime of x. Remember, f prime of x is the first derivative. And actually, where is it differentiable? So in your mind, you need to do f prime of x. All right. So f prime of x, we're going to apply our first principle again. So first principle says limit as h tends to 0. You need f of x plus h. But in this case, remember your function there's absolute value, so it will be absolute value x plus h minus f of x, which is just the absolute value of x all over h. But now we know already that we're looking at the first case where x is greater than 0. So in that case, absolute value x plus h will just be x plus h. So this guy there will just be x plus h. And then our absolute value of x will just be equal to x. If you simplify that, notice you just have limit as h tends to 0 of h over h, which is 1. All right. There you already have like 2 out of 5 marks. Let's keep going. So in conclusion, we can say, so f, the function is differentiable for any x greater than 0. Remember, this limit exists, all right? We found the limit and it gave us some value, right, of 1. It means that it is true for all x greater than 0. So the function is differentiable for any x greater than 0. But do we stop there? The answer is no. We need to look at the situation where x is less than 0, all right? Why? Because it's an absolute value function we're dealing with. So we look at x less than 0 now. When x is less than 0, absolute value of x becomes minus x, right? Again, you choose some small h value such that if I add x plus h, it's still negative, so it's still less than 0. So absolute value x plus h is going to be minus, this time, brackets x plus h, all right? Therefore, we say for x less than 0, we apply first principle again. F prime of x, limit as h tends to 0, x plus h absolute value, minus absolute value of h. Take note, this absolute value there becomes minus x plus h. Absolute value of x is minus x, all right? And if you simplify, take note, the minus x will cancel with the plus x. You're just left with minus h over h. Some of you usually make mistake with the sign here. You stick at 1. I don't know why. Please do the math properly. Keep the negative sign out and put everything in brackets. All right. So this limit here obviously gives us minus 1. Again, we can say that so f again is differentiable for any x less than 0. You see? So x is differentiable for x greater than 0. So from 0 to infinity. And x is also differentiable for x less than 0. It means from minus infinity all the way to 0 without including 0. If you notice, there's only one thing left to be done, to check what happens when x is actually equal to 0. Because we've seen that it's differentiable for x less than 0 and for x greater than 0. But now we want to see what happens when x is actually equal to 0. So let's see what happens. All right, when x equals to 0, you plug it again, first principle. So we're looking at f prime of 0 this time. Now remember, x equals to 0. It's almost like finding the slope at the point, all right, or derivative at the number. So you don't have to say f prime of x because this time you know x is 0. So you say f prime of 0, limit as h tends to 0, f of 0 plus h minus f of 0 by h. Obviously, if you simplify this, take note, you just left with absolute value of h over h. So you end up with something that looks like this if you simplify. But now, to test this limit, you need to test from the left and the right, all right? You need to take the limit as h approaches 0 from the right. And remember, when I say 0 from the right, it means absolute value of h is going to be equal to h, all right? In that case, the limit is going to be 1. Again, you need to test the limit as h approaches 0 from the left. And what does that mean? It means h is typically negative. Therefore, absolute value of h here is going to be minus h, and then you have negative 1. Now, the fact that the limit from the left and the right are different, what does that mean? It means that it does not exist, all right? So we can say that f is not differentiable as 0, all right? So we say since these limits are different, remember for f prime of 0 to exist, it means that the limit from the left and the right was supposed to be the same. But in this case, because the limit is different, f prime of 0 does not exist. So in conclusion, the function is differentiable everywhere except at 0. And if you want to write a formula of f prime, that's what I usually do in my test. I'll say, give me a formula of f prime. And some people think I'm asking for first principle. No, give me a formula of f prime. You've already solved it, right? You saw that when x is greater than 0, your derivative gave you 1. All right, we've done that already. And when x is less than 0, the derivative gave us negative 1. We can even sketch it graphically. There we go. That's a graph. You see, for every x value greater than 0, there we go, you get this top piece here. And for value less than 0, you get minus 1. But as 0 itself, you see, when you approach from the right, the limit there gave us 1. When you approach from the left, the limit gave us negative 1. You see the open dots there to show that that limit doesn't actually exist. Guys, I'll stress again, example 3 is a must know. You must know, all right? Now, if you look at the actual sketch, so now we're just looking at the sketch of y equals to absolute value of x. This is what it looks like. You can see that the point at this origin here, it's like a V junction, right? It's a sharp junction. So slope doesn't exist there, all right? So we're going to see all the possible situations where slope does not exist. By definition, we say if f, this is very important, it's a theorem which you need to know. If f is differentiable at a, then f is continuous at a. I'll say it again. If a function is differentiable at the number a, automatically it is continuous at that number a. Not the other way around. If a function is continuous at the number a, it's possible that it's not actually differentiable at that number, all right? So the converse does not hold, all right? The converse is false. So watch out for stuff like this because I like MCQs. How can a function fail to be differentiable? So let's look at possibilities. All right, look at this first curve. It almost looks like our absolute value curve. You have that sharp V junction there. So this is like an upside down V. So this sharp point here, definitely it will not be differentiable. Once you have a sharp junction, it is not differentiable. Obviously, if you have something like this as well, this is actually a discontinuity. So for a corner, it's not differentiable. For a discontinuity, you know already it will not be differentiable because the limit from the left and the right is going to be different. Also, if you have a vertical tangent, all right? So if you have a vertical tangent, it's also not differentiable at the vertical tangent, all right? Higher derivatives, what does higher derivative mean? So far, we've only looked at f prime of x. Higher derivative means we're looking at f double prime, f triple prime, so second, third, fourth derivative, and so on, all right? And how does the notation look like? So if I take f prime of x and I differentiate it again, I get f double prime. So this one is called second derivative. I'm sure everyone knows that. You're smiling because you know already. In Leibniz notation, we say d dx of dy dx is just d squared y dx squared. So you can say f double prime, or you can just say d squared y over dx squared. It's the same thing, all right? I will not force you to use Leibniz notation or not to use Leibniz notation. If I say find second derivative, just use f double prime or use d squared y over dx squared if you want. Now, how are we going to look for the second derivative of this function? You need to start by getting the first derivative, all right? I think this is an example that we've done already. You start by getting the first derivative, and then you differentiate that first derivative again. In this case, using first principle, if you simplify, let's see what you get. You get 6x, all right? So I'll mention again and again so that it sticks. If I say differentiate, find the derivative of this function using first principle, it means use first principle. So if you don't know what first principle is, automatically you have zero for that question. I won't even mark it. In fact, it's just a zero, all right? But if I give you a function and say find the derivative, and I don't specify, all right, use any method that works for you. If it's first principle, any method, all right? All right, this is a more higher derivative. There we see f triple prime for third derivative. This is just d cube y over dx cube. It can keep going on and on forever. You can have fourth derivative, fifth derivative, and so on. All right. This is now the n derivative, all right, where n can be any integer, any positive integer value. All right. And that brings us to the end of the lecture.